Yeah, hi, my name is Malte. I'm working for Blue Yonder, and I would like to talk to you about paradoxes in model training and evaluation under constraints. So those are paradoxes that I encountered in customer projects. I'll be talking about unconstrained probability distributions that will look quite familiar, about constrained probability distributions that look a bit funny at the beginning, but we'll get into that in a moment, and a lot about strawberries. Because strawberries, that's our leitmotif. We are talking about forecasting strawberry box sales. So we're not selling the strawberries by the kilogram or the pound or the piece, but by boxes. And strawberries are a great example for an ultra fresh product. So unfortunately, they need to go to waste in the evening. The strawberries that came in the morning are either sold or they go to waste. So this is our forecast for the number of sold strawberry boxes. And when the actual sales come in, they look like this. And we are a little bit unhappy about it because it looks like we have a systematic overforecasting overall, and especially in this time range here. It seems that our model is not particularly good because it didn't find at all that on this day and on that day, nobody bought any strawberries. We would look into the model, we would look at features, at the data, until we eventually look at the process and ask the question, maybe the strawberries just went out of stock and there were no more strawberries to buy. To check that, we can superimpose the capacity. So now in orange, we have the capacity that was set in the morning, so the number of strawberry boxes that were available for sale. And when the capacity was hit, so when strawberries went out of stock on that day, we have a red dot here. So we see that we ordered systematically too few strawberries here, and feel that in the number of sales. And on those days, it's not that nobody wanted to buy strawberries, but there were simply no strawberries delivered in the morning. So we see that it's important to distinguish between the unconstrained demand forecast, so like how many strawberries are being asked for by customers, and the constrained demand, that is the sales, so the strawberries that are eventually bought by customers. And that's the difference. So this is a situation that you will often encounter in retail. And of course, you want a meaningful training and a meaningful evaluation that takes into account the constraints. And getting there, involves a little bit of probability theory, a little bit of expectation values that sometimes take slightly convoluted expressions. And of course, what you want to have is a shortcut here. But what I would like to convince you in this talk is that if you try such a shortcut very often, it will be quick, but it's a bit too dirty, and you'll end up with a simply wrong training and a wrong evaluation that will mislead you. And I'll try to convince you to take the slightly longer route, and that this route is actually not that complicated. So I will first introduce our workhorse. So these are the upper censored probability distributions for constrained demand. We'll learn why this shape is what it is. We'll then see what can go wrong when we train models on constrained demand, and finally, how to evaluate models on constrained demand. So let's start with upper censored probability distributions, and with the question, what does a demand prediction of 9.7 strawberry boxes actually mean? Because we don't want to say that on a given day with such a prediction, you will sell 9 strawberry boxes plus 0.7, of course, but implicitly what we mean is that the expected mean demand on such days will be 9.7, and what is implicit and is taken here to be the Poisson distribution is that there's a certain distribution of what the demand could be. So we are assigning every demand value of a number of sold boxes a certain probability. Now, this blue line here is the expected value of the unconstrained distribution. If we now have a constraint, then things change a little bit. And here, this is what you would see, the sales at a capacity of 13. So for 12 and below, we don't have any change here. But since we can never sell 14 or 15 or 16 or 17 boxes of strawberries, all the probability mass of these events is added to the probability mass of selling 13 items. So a sales of 13 could be due to any demand being 13 or 14, 15, 16, and so on. And this is why it's called a censored distribution. We are censoring information. When we observe 13, we don't know whether the true demand was 13 or maybe 20 or 25. So let's have a look how the capacity impacts the expected sales in the situation. I keep the expected demand to be 9.7, so I have always the same stock or the same situation, and I'm actually changing the stock. So I'm going from a capacity of 0, no stock at all, to a capacity of 25. And when this capacity is very small, then we are very likely to just sell all of it, and my expected sales match my capacity. When the capacity is very large or much, much larger than the expected demand, well, then I will just sell those 9.7 on average, and the capacity doesn't really matter. And then I have some region in between, which is quite interesting because here sometimes will hit the capacity and sometimes not. And I can make this more explicit by looking at this capacity hit probability, or like the out of stock probability. This is very high when the capacity is low. So if I have a capacity of 0 or 1 or up to 5, then I'm very likely to hit this capacity, and the constraint distribution looks like this. So with 96% probability, I will sell 5 items, which is saturating this capacity. In between, like for a capacity of 10, I have a 50% chance to hit the capacity. The expected sales are shifted a little bit to the left, down from 9.7 to 8.6, but I can still see part of the probability distribution here. And if the capacity is very, very large, so much larger than the expected sales and like beyond any reasonable value in that probability distribution, then it doesn't have any impact anymore on my sales. So you can barely see that the probability to sell 21 was pushed down from a finite value down to 0. The probability to sell 20 was slightly increased, and if you round it down, then this is still equal to 0. So now we have all the ingredients, but what's also important to acknowledge is like the order of which they appear. So in practice, you would use an unconstrained demand forecast like this one to actually set the capacity. So this is the input to the planner, who then decides, okay, on that day, we want 50 boxes of strawberries or 75 or 110 or so. And this capacity, together with the unconstrained demand forecast, can then be combined to get the constrained sales forecast. So we have a rate, a mean rate. We then also have the capacity, which itself depends on this rate, and then probability distribution for the number of sales, which has this particular shape here because of the censoring. And in practice, or what we will observe, is a random sample out of that constrained probability distribution. And we see that what we want to learn, namely this, is quite far away from what we eventually observed, namely the constrained sales. So let's see what that means when we train models on constrained demand. So we might run into very different situations here. So the first situation is that the capacity is just hit every day. Well, then we never know the true demand, because we never know if there has been only one unhappy customer, or maybe no unhappy customer at all that didn't get to buy strawberries, or maybe there were hundreds of customers who didn't get to buy strawberries. And thankfully, this will not happen in practice if you have a sufficient supply, because you would have so many unhappy customers. What the data scientists really like is if the capacity is just set to a very, very large value, and we are just so certain to never hit it, to never go out of stock, that we know that sales reflect the true demand. This is nice for the data scientists, but compliance and sustainability and finance departments will come and say this is not a viable solution here, because so many strawberries need to go to waste in the evenings. So what we will deal with in practice is the capacity is hit sometimes we see the true demand, so a mixed situation like that one. It's unavoidable to go out of stock from time to time if you want to avoid lots of waste. It's unavoidable to sometimes have some waste if you want to avoid going out of stock every day. And we see the first dilemma here, that is the situation that is optimal for operations that you like as a retailer, because it is the balance between out of stock and waste. This is not optimal for data science. I mean, data science wants to be in that situation here. And in projects, what I often encounter is that people say, let's not split hairs, and let's just use the constrained sales as an approximation for the unconstrained demand. It's going to be fine. It's going to be okay. But if you do this, then you get an under-forecasting model, and you get more and more capacity hits, and this is not really the way you want to go. So why is that? Well, let's look at this example again. A true demand of 9.7 at a capacity of 10. If you repeat this many times, you would expect a probability distribution like that one, from which we want to learn the unconstrained demand of 9.7. But if you just interpret this as true demand, you will learn the expectation value of this constrained distribution, so namely this red line here, which is at 8.6. So it's not a viable way to just say the constrained sales are a good approximation for unconstrained demand if you hit the capacity more than a couple of times. The next step that I often encounter is that people then say, oh, let's just train on the days on which the capacity was not hit. So let's truncate the distribution in technical terms. Let's remove all those capacity hit events and keep all the green dots and train on that. And if you do this, and you again have a substantial amount of out of stocks, you will keep decreasing the forecast and run into even more out of stocks. So you again get an under forecasting model. So why is that? Let's go back to the example. Truncation means I'm actually removing this data point from my training set. So I'm training on this left-hand side of the distribution, which has an expectation value which is even further to the left at around 7.5. So instead of learning what we want to learn, namely 9.7, we learn something much smaller, around 7. And the reason for that is that if we do the selection here, we're inducing a bias by the selection procedure. We are getting a hindsight bias that will then reflect in the training. That is, if I select days on which the capacity was not hit, I'm automatically selecting days with a lower than typical demand. I'm selecting days on the left-hand side of the probability distribution. So I really need some methods for truncated data, for example, stats models. So let's now assume that we train the model on constrained demand and apply the correct procedures here. We will then want to evaluate them and ask whether everything worked out fine. And the main question that I would like to look at here is the model biased? I mean, we want to avoid to have a biased model because we want to have the right balance between waste and out of stock. And how to not evaluate it is pretty clear. If we just hold the mean observed sales against the mean unconstrained forecast, they will differ very much, and it's hard to say how much they should differ. And we already know the solution to that. I mean, we need to compute the expectation value of the constrained distributions instead. So we need to make this constraint explicit to then see whether it matches the mean sales. And what I often encounter here is that people ask me, oh, why do we need to do this in such a complicated way? Because in our system, we don't even have the exact capacity. We don't know whether we have 50 boxes of strawberries in the morning or 60 or 70. We only know whether in the evening we went out of stock or not. So the only thing that we can do is we can segregate by capacity was hit against capacity was not hit. Please, let's do that and evaluate from there. And if you do this here, you again see that these numbers simply don't match, even though everything in this talk is always a perfect forecast and everything like in a toy model. So again, the mean actual sales and the mean unconstrained forecast, they don't match, neither in the case when I select days with capacity hit, nor when the capacity is not hit. So why is that the case? Well, again, we are just inducing a bias when we select on hitting or not hitting capacity. So if I ask for the expected sales when the prediction has a certain value and the capacity is hit, if I evaluate that, well, then I will just find the capacity itself. So I will not learn anything at all about the forecast quality. In that case, I will just reproduce the capacity setting strategy for the days on which I have hit the capacity. So I'm really not learning anything at all about my forecast. If I condition on not hitting the capacity, I can write down the expectation value and get some convoluted expression here. But the important part is that the expected sales will always be smaller than the predicted mean. So we will have the impression that we are over forecasting, but the gap actually depends on the capacity itself. So again, we have a very, very strong dependence of the numbers that we see on the capacity that we have set ourselves in the system. So without knowing how we have set the capacity, there's no way in saying what we should expect from these numbers and what is the right number to compare it to. So we know we need to compute the expectation value under constraint, and in this case, it then turns out to be 18.18, which nicely matches the mean sales that we also observe. And what then often happens in projects is that people say, okay, we are convinced that the model is globally unbiased. I mean, on global level, this works out, but I still doubt that all these capacity hits are necessary. I mean, I still think that on the days that the capacity was hit, there was some under forecasting, and this is why we have hit the capacity. So let's do this segregation again and look at the data by only capacity was hit or only capacity was not hit. And let's now look at the mean constraint forecast. And if you do this, you will see that again, it does not match the mean sales. This difference here is actually significant. And so again, we can't have the expectation that the mean sales matches the mean constraint forecast if we have grouped by that. And the reason for that is, again, that if you select by the capacity was hit or the capacity was not hit, you are selecting atypically large or atypically small demand values, and these are not representative. So again, you are like selecting rather the left-hand side of the probability distribution or the left-hand side realizations of the probability distributions or the right-hand side realizations of the probability distribution. So you don't have an unbiased sample here that you're evaluating. So the bias that you see might very well be induced by your selection procedure and not by the model itself. So still, it's very, very valid to ask the question, do we have out of stock under control? Do we hit the capacity as often as necessary, or are we totally blind with respect to that? And I would like to propose to evaluate by predicted capacity hit probability. So how would we do that? So in this scatter plot here, I have on the x-axis the predicted capacity hit probability for all the different days in a large synthetic data set. So that probability can be anything between 0 and 1. It's a continuous variable, so any value in between is allowed. And on the y-axis, we plot the actual capacity hit. And that's a binary variable, so it can only be 0 or it can be 1 and nothing in between. And now from this scatter plot, you can't really learn too much. I mean, if we predict, say, 0.5, then sometimes we hit the probability. Sometimes we hit the capacity, sometimes we don't hit the capacity. To evaluate whether those probability predictions make sense, we can first aggregate over the entire data set, so take the mean over all predictions and all outcomes, and then validate that we predicted a bit more than 80% of capacity hit overall, and we also observe a bit more than 80% of capacity hit. And if you want to dive a little bit deeper, what then makes sense is to bucket the data into buckets of very similar capacity hit probabilities. So here we have the bucket of capacity hits around 5%, so predicted capacity hits of around 5%, 10%, 20%, 30%, and so on. And essentially, we have a binary classifier here, and we can evaluate this binary classifier. So when we predict 40%, we expect to see 40% of capacity hits. And for this synthetic data set here, this is actually the case. So the size of the bubbles here reflects how many events are going into the respective bucket. So we see that most events here are at a very large capacity hit and just a few here. And so this is the picture that you expect when your model is perfect. And very much in general, it makes a lot of sense to be forward-looking when you evaluate forecasts. So take the prediction, group them by some criterion on the prediction, and then evaluate the mean outcome per prediction, because that's easy to compute. Often one starts to do backward-looking things. So one selects extreme outcomes And one is then surprised that these outcomes were underestimated or overestimated. But by selecting those extreme outcomes, we are again selecting the left-hand side or the right-hand side of the probability distribution. So we are inducing a bias by selecting by outcome. So this brings me to the end of my talk. I have a few take-home messages. The most important one is, of course, please take constraints seriously. If you have a finite capacity, don't ignore that. Don't set demand equal to sales unless you are really, really sure that you never hit the capacity, and capacity is not a problem for you. When you evaluate, group by prediction, don't group by outcome. So in other words, don't look back from an outcome, what could have led to that outcome, but look forward, given a set of predictions, does what happens eventually match these predictions? And think probabilistically. If you ask questions like, how likely is it that we run out of stock? Or I want to order as much stock that my out of stock probability is pushed down to 2% or to 1%. If you ask such questions, you need probabilities, you need probability distributions. You will not be able to deal with such requests using just a point forecast that gives you the best estimate, but does not make any statement about the distribution. Yeah, and finally, simulate the ideal clean case first. Everything in this talk was within a sandbox-like toy environment. I took one very simple distribution, the Poisson distribution. Everything was under perfectly controlled conditions. And even here, at least my intuition was sometimes challenged. So I think we first need to understand like the simple case, and then we can go out there into the actual world where, for example, retailers will tell us, well, we don't know what is the start capacity on a given day, and we'll very often not know did we really go out of stock or not. Maybe also some strawberries are being stolen, and many other real-world complications that will make data science challenging but also fun. Yeah, I hope this was useful for you. If you have any question, please feel free to ask them.
We got a question. I'll go ahead and show it on stage. Do you recommend any Python packages for this sort of truncated distribution analysis?
Yeah. So stats model has a fitting method for truncated distributions, indeed. There are, unfortunately, while most commercial packages also offer fitting of censored distributions, I haven't found any Python package that does that. I wanted myself to maybe add to SciPy to at least have the censored distributions handy, that you can work with them in SciPy. Yeah, so stats models would be the first starting point. Yeah, but I hope that there will be some more open source contributions in the next month or years.
And then another question from Julia. Can solvers accurately predict this?
Yeah, so I mean, you in a sense, when you censor, you are always removing information. So there is, I mean, you have, from a data science perspective, definitely a worse situation when you have a finite capacity than when you have a full capacity. I mean, everything here was like under full control, and essentially we knew what was the truth. So yeah, I mean, you can work around censoring and truncation, and you can work with maximum likelihood techniques and so on. But yeah, you will have a worse model performance if you have finite capacity. It's removing information. The information is gone. Yeah, you can circumvent it to some extent, but not perfectly.